Hello, and thanks for tuning in. Today we'll titrate potassium permanganate with hydrogen peroxide. A novel pipettor will be used to conduct the experiment. We'll go over preparation of materials and labware, then conduct 3 titrations. Once our data is recorded, we will calculate the molarity of potassium permanganate. First, begin by creating 30 to 40 milliliters of potassium permanganate and water solution. Add an arbitrary amount of crystals to a flask or beaker so that we can create an analyte of unknown molarity. Now insert 2 reservoirs into the silicone base provided with TriaDart II. Add funnels and then fill each volume with up to 10 milliliters of the respective reagent. Pick up each cartridge with a fitting located on the pipettor body. To ensure that no fluid is lost due to a buildup of pressure, please depress the associated bellow in advance. Let's attempt to prove or disprove our initial assumption for this experiment, which is equal volumes of potassium permanganate and hydrogen peroxide will neutralize each other. Dialing in a 1-to-1 ratio for the 2 chemicals and creating a small sample demonstrates that this is not the case. The titrate, hydrogen peroxide, is much better able to reduce the analyte at a 1-to-1 ratio. Before proceeding with the first titration, please record the initial fluid volumes. We will focus on increasing the proportion of the titrate in an acidic solution dominated by the analyte. We will be dispensing the titrant B and analyte A simultaneously, setting our pipettor to produce a ratio of 1/4 B to 3/4 A. A new ratio, more biased towards hydrogen peroxide, is selected. Having dispensed the new reagent volumes and agitating the solution, we do not observe any significant change in color. A yet more hydrogen peroxide heavy ratio is selected. Now the reaction is progressing towards a redox point. Oxygen gas is being produced at a slower pace as evidenced by the froth or bubbles. More agitation of the solution is required and gradual color change can be observed. Finally, a stable, pale pink solution can be observed. This is our stopping point. We'll use a ruled card to read the volume remaining in each cartridge. This card may be found in TriaDart II's instruction booklet, available as a PDF on our website. By the way, we want to thoroughly rinse all equipment with water between titrations. We'll start the second titration by dispensing roughly 1/4 of titrant to 3/4 of analyte by volume. There is no need to experiment with a 1-to-1 solution anymore, so we'll start with only sulfuric acid in our flask. We'll perform a total of 3 titrations for a more robust data set. A variance of 5% is expected in the resulting volumes. Wanting to produce an even paler pink and not taking into account the rate of progress, the experimenter dispensed a bit too much hydrogen peroxide. However, a quick recovery was made with a controlled addition of an analyte heavy mix after a further ratio adjustment. By the way, performing this experiment forwards or backwards yields analogous results. Here we present the third titration at double the normal speed. A good understanding of technique, the properties of the reagents, and the tool set demystifies this procedure. Is it possible that a new tool will make titrations go this smoothly? Seriously though, let us take a minute or two to remind you of lab safety. Be sure to wear gloves, safety glasses, an apron, and to have adequate ventilation. Keep a jar of baking soda nearby as you might have to neutralize the sulfuric acid. Never add water to acid. Instead, add sulfuric acid to a mixture of water and baking soda. Don't flush anything down the drain without proper inactivation. If you cannot chemically neutralize the discards, please dilute them with generous amounts of water. Our experiment has yielded the following results across 3 iterations. These experimental value pairs are equivalent by mutual ratio, which varies in the range of 0.24 and 0.28 to 1 with respect to the principal reagents. If necessary, the second and third titrations can be performed by dispensing each reagent independently using the single fluid pipetting scale. This alternative approach may produce a more literal agreement of volume readings between titrations. Now, let's discuss the nature of the redox reaction in question. The accepted molecular equation advises that combining 2 moles of potassium permanganate, 3 moles of sulfuric acid, and 5 moles of hydrogen peroxide yields 2 moles of manganese sulfate, 1 mole of potassium sulfate, 5 moles of oxygen, and 8 moles of water. Our experiment is directly concerned with the reaction of hydrogen peroxide and potassium permanganate. The former acts as an oxidizer and the latter as a reducer in this context. The equation detailing a balanced interaction, or redox of the 2 components, appears at the bottom of the slide. We'll use this equation to solve for our chief unknown, the molarity of potassium permanganate. Please review each term of the equation, then the fashion in which its terms are rearranged to solve for CM1. Plugging in the known values and crunching the numbers, we understand that our unique solution of potassium permanganate has a concentration of 0.187 moles per liter. In summary, we've successfully determined the molarity of our analyte using a compact analyzer, which is parametric, precise, and fast. You can get started with nearly any analysis task when you invest in a TriaDart II, a flask, some funnels, and a beaker. Our system is filled and ready to go in just 3 steps, and as you have seen, they all take place on your desktop, never near eye level. Please consider this and other products designed and made by H2O2 LLC. We pour endless attention into functionality, ergonomics, and fulfillment of our products. Please visit our website, listed below and linked in the description. At H2O2.com, you will also discover our nanomembrane-based protective respirator, RipMask 4. Thank you and hope to see you again.